Hello, my name is Microstrip. I'm from Instituto de Telecomunicações and Instituto Superior Técnico, University of Lisbon. The topic of this module of the online course on microstrip antennas is the Predesign procedure. Having defined the antenna specifications such as central frequency, bandwidth, input impedance, gain, polarization, and others, the Predesign procedure is composed of 3 steps. The first step is to choose the adequate substrate, meaning the relative dielectric constant, the loss tangent, and the thickness. The second step is to estimate the patch dimensions, width and length. The third step is to estimate the feeding point location, x0. To reach the first step of the design that appears after the predesign, we need to fine-tune the predesign procedure using a software package. There is a large variety of substrates and substrate manufacturers. Rogers is a well-known manufacturer of microwave substrates. The quality and cost of a substrate depends on the relative permittivity value, the losses, the homogeneity of the material, the thickness accuracy, mechanical properties, thermal properties, and so on. Concerning losses that are represented by the loss tangent, the lower the better. This is critical mainly at high frequency, but low loss substrates are more expensive. As the relative permittivity decreases, the efficiency and the bandwidth increase. As the thickness increases, the bandwidth increases, but the efficiency decreases. Thicker substrates are more expensive. For antenna applications, low relative permittivities are better, and the thickness is usually chosen according to the required bandwidth. The substrate relative permittivity and thickness have a major impact on the impedance, bandwidth, and radiation efficiency, as shown in this figure. So the impedance, bandwidth, and radiation efficiency can be estimated from the curves presented. We can derive linear approximations for the impedance bandwidth associated with low, meaning 2.2, and high, meaning 10, relative permittivities. The patch dimensions are chosen with a process that is initiated choosing a value for the width of the patch, that is lambda over 2 multiplied by the square root of 2 over the relative permittivity plus 1. Then, having defined this initial value of W, we can calculate the relative permittivity of the equivalent homogeneous media using the formula already introduced when we studied the microstrip line. Then we can calculate in step 3 the fringing field effect. And then the equivalent length of the patch, and consequently, as we have the equivalent required length and the fringing effect, we obtain the physical length of the patch by subtracting LE by 2 times delta L. For a square patch, we need to repeat this procedure And we can use an iterative process starting in 1 and going up to 4 and repeat it using to initiate the step 1 with a width that is equal to the length obtained in step 4. After a few iterations, the convergence is reached. Having defined dimensions of the patch, we can now calculate the feeding point location. First, we need to calculate the radiation conductance and the radiation and the resistance at the border of the patch, R0. And then, using the formula obtained in the transmission line method, calculate X0. Let's show an example to better understand how this pre-design procedure works. So consider that we want a square patch with central frequency 10 GHz. We require a bandwidth of 6%, meaning that we need coverage from 9.7 GHz up to 10.6 GHz and input resistance of 50 ohm. We choose a good substrate, a Rogers RT Duroid 5880 with dielectric constant 2.2, loss tangent at 10 GHz of 0.0009, and we have estimated the thickness of the substrate according to the previous indicated criteria taken from the figure of the bandwidth as a function of h over lambda 0, and we reached a thickness of 1.575 millimeters. This thickness is the standard thickness offered by the manufacturer, that is larger than the minimum thickness necessary to reach this 6% bandwidth. Then, if we want really a square patch, we need to proceed with this iterative process. And as you can see from the table shown, after 4 iterations, we have reached convergence. So, in the 4th column of this table, you can see that the values are really close to the ones that exist in the table 3 of the same table, in the column 3 of the same table. So we have reached a bandwidth of 7.9%, a directivity of about 7 dB, efficiency, radiation efficiency of about 83%, and gain of about 6.2 dBi. Now we need to confirm this pre-design parameters using a software tool. In this case, we used an old software tool, Ensemble, to check the pre-design dimensions. As you can see from the S11 curve shown in this figure, the agreement is very good. There is a slight detuning of about 50 megahertz, which is really small. We get a bandwidth with S11 less than 10 dB, minus 10 dB of about 6.3%, which is good. We required 6% in the specifications. And the gain at 10 gigahertz is about 6.85 dBi. Also, the radiation pattern shown in these figures show the typical behavior predicted by the cavity model. Very wide coverage of the upper hemisphere and no cross-polarization in the broadside direction. Goodbye.